And you know how it goes. They have a midterm just like you, and I've been asking for if they had any questions or stuff for like a few days, and no questions until until the exam's due soon. So they suddenly barrage me after the class with quote unquote quick questions. Okay, but speaking of the test, I need to cover something in a hurry here that's on the test. Okay, and I don't know which problem it was, but it involves the sum of a couple of normal distributions, and it's just critical, and I have to do. I don't like doing it because I want to fill in some other holes, before, but I have to. The test is around the corner. I got to do what I got to do. So hopefully I can make some sense out of that. Let's expand the screen here. So, but before, were there any other? Sometimes somebody has a quick question on the statement of a problem or something on the test besides this one with the sum of the two normals. Was there any other? I should know, that way I can be thinking in the back of my head what's critical to do today. Was there another problem that was causing trouble? The one with what was the one? The red balls and the white balls. That's just time consuming, right? I mean, it's not. You're okay with that, right? Ames looking like.
Oh wait, I'm wondering which problem is that?
That's where you want to produce the joint density distribution for x and x.
Oh, but okay. The wording of the problem was functional and defective, but whatever.
All right, right. Get that better memory than
working
mine.
On the test.
Yeah, because so I think it was transistors from the book, so I kind of at least used the book thing, but I don't know. I just think that takes time.
Interesting. But
most of the matrix is zeros, right? So it's you can right. There's work to be done, but a lot of zeros, right? I mean, if it takes 6, how many shots do you get? 6 pulls to get the first one. That can't happen because you only got 6 transistors. So in 6 pulls, you're going to get both. So you can't have one.
Well, in that case, I might need to have clarification because the way I read the problem was find the probability of it taking the probability of it taking 2 tries to get to the first one, and then an additional 2 tries to get to the second one.
That would be
and you do that for every single one.
That would be PXY 2. Right.
Right. Okay.
Yeah.
I'm just making sure that was what the question was. Is do that for all of the individual options.
The matrix has it's 1 through 5, right?
Yeah, we went ahead and just said 1 through 5 because
but that's
by the 6th time. Yeah.
Look at this one. 5. It can't possibly take
0. Yeah.
Yeah. It can't. So there's a bunch of easy kills there. So I'm going by area, uniform distribution. You can probably get 69% of the credit by just getting those zeros in there. I mean, if I'm being fair, uniform. So yeah, it's just time consuming. Somebody can be delegated to do that if they've been bad. But okay, so that was one problem. Well, let me try to get to that normal stuff. It's not going to be pretty because my big thing was yesterday I presented my committee work, and it didn't go that well. I guess it went okay. But anyhow, so what are we talking about here? It's a joint distribution probably, but we're dealing with some function of a couple of random variables. And this is a non-trivial thing. If, for instance, if x was uniform, 0, 1, and y was also, but independent, they're independent. It's a legitimate question to ask if you simulated this, what would the histogram start looking like? Okay, so we're going to think about this. So one of them, what do these distributions look like? Just height 1 here. So if I'm looking for the distribution, which is a a way of saying, give me the density function of x and y. The distribution of x plus y, the sum. It's a legitimate question of what shape. Is it just going to be a bigger one here? Because if you get x plus y, that it's potentially you could get 2, right? You could get up to 2. But the question is, and it's a legitimate question, what's the spread of the numbers you can get out of this? Remember, this one goes in 0, 1, this goes in 0, 1. What's your spread? So this is like just x. But if I've got, I don't want to be in the washout. But if I've got x plus y, what's the space? If you want to use a fancy word, they say the space of the variable, the support of, what's the support? The space is 0 to 2. The support is 1. So you could get values between 0 and 2, but is it just going to be a plateau? What are you going like this? But how do you know that? Except this is not. Maybe it's just me, but I feel that this is the critical thing, and it's not. This is the easiest kind of function you can get of the easiest random variables, and I'm telling you, it's not obvious. So, but it's going to have the same mean, but it's going to be what? It's going to be a triangle. With what height? This is the same mean at 1. And how do we know that this is a density? Obviously, the area is 1. Well, this is, if you look at 1/2 base times the height, you end up with a 2 here. So that's messed up. I got to get a 1 out of this. So hold on a second here. This is something. Okay, 1/2 base. The area has to be 1. So let me. What's going on? The thing is you don't. The height, the actual height. Okay, the height should be. Now I'm getting confusing myself. The height should be 1. The middle, the mean actually is, for each of these, the mean is 1/2. So if I'm adding 1 to the other, we would expect the mean to be 1, okay? So the mean is 1 here. This is a 1. So anyhow, this is the density curve. So now let's take the area of that again. Let's see if I can get it correct this time. So this is a 2. So it's 1/2 base times the height. That should be 1. But you might say, how do you go from this shape to this shape? Well, that's a mystery, right? I think it requires something called a convolution or something. And if you take n of these independent random variables, do the same thing, and if you divide by n, so in other words, you're taking the mean, okay? The shape you get will start looking like a normal curve. It's very interesting, okay? So you might say, I don't see a normal curve. Well, this is a lot more normal looking than this. It will continue to look more so when you take more of these random variables. So this begs the question, and of course I could be a little off base in trying to say this, but what distributions would be resistant to that there are some, changing the way they look, okay? So if things are going towards normality, normal shape in the density, well, what if I started with not uniform, but something else, what do you think it would be so that it doesn't, it's still, it still looks like a bell-shaped curve? Was that too much of a question to ask? What do you think? I mean, what could it be? We've only looked at so many. If everything's heading towards a bell and you start with bells, you're going to end up with a bell. Okay, that's just the way it is. Okay, but the amazing thing about this, this went to this. These could, if you took enough of these, like 10 of them or something, if they could be anything, they could be the beta distribution. Okay, and if you averaged them, sample from them, you end up getting a bell. It's absolutely amazing, okay? So let's try what is the theorem that we need to take this darn test with? What do we need for the test? Because it's going to be the distribution of x and y, but what is our x and y going to be? So this is normal, what parameters?
Mu1 sigma squared, sigma 1 squared.
I finally found the reason why he has sigma 1 squared instead of the standard deviation. Okay, it took me this long to realize that there's reason to the madness why he did it this way. And this is normal with mu2 sigma 2 squared. Okay, what do we expect would happen here? What if they were the same bells like this? And you're going to add them. The mean here was 2, the one here was 10. If you add the data, you expect it to be 12, okay? You just expect that. As far as the variance, no, that's not this. What's the theorem for the variance? It's the sum of the squares, right? Adults are, it's the sum of the squares. So this is going to be normal. We're going to add the means, and it's going to have variance, the sum. I hope we appreciate the fact that by using what we use in Math 140, GE stats, it would be sigma 1 and sigma 2. That's not, this is simpler to be able to write this down. Okay, so how does that apply to our problem? Well, let me see if I can get my notes. It's been a rugged day yesterday, so let me find the problem that's not exactly the same.
I feel like that's enough. Like that does give us the information we need to do that problem.
Yeah, but I feel like I should do a problem with this. I feel like I should. I don't know. I just I don't like the idea of. I think you're supposed to, when you, in general, give a test. Ideally, we've done one similar to it. I don't want something too similar. So, looking at. I'm looking at 3C, which has a few parts. So, okay, so 3C, I'm going to have to use my glasses. What's the story here? It's sort of a long-winded story, but it's a good problem. So a basketball team has a 44 game season, which that sounds like an awful lot. I don't know if it's a college team. How do they find time to play 44 games? I don't know, man. There's something not quite right about this. I mean, what the NFL season's what? I mean, even the Lakers. I don't know how many games they play. 70. Well, they're professional. So 26 games. So out of the 44, so 26 are against A-listed teams, and 18 are against B-listed. And the win percentage for against the A-listed guys is 0.4, and against these guys, these lesser teams, is 0.7. And W is discounts the number of wins in the season. All right. Okay. So we want to calculate something really simple here, and I hope I get this straight. We just want to get the probability that the total number of wins is greater or equal to 25. Okay, so this is really truly a sum of binomials. It's just two things going on here. When they're playing the A-listed teams, the success probability is one thing, it's 0.4, and the other ones it's different. So it's really this problem fits into a sum of binomials, which we didn't cover. But since we're gonna use a normal approximation each of those binomials, then okay, now I can apply this thing down here. So let's. In order to make this normal approximation, I've got to get the binomial mean and variance. So how to do that? So let's see that if I do the Washington. So x. So this is binomial, and this will be. We'll count the number of wins against versus the A teams. Let's see if that's, it's versus A teams. And this is the binomial, is number of wins versus the B. So these binomials have parameters, right? So it'd be nice to know the mean and the variance. Okay, so for the A, the mean is what? It's NP, right? So how many? So that was 26. So I'm trying to just scratch calculate this right here. So the mean for E, I'm going to have to erase this as soon as we do it, but I got to calculate it. This is a review of binomial mean. So it's just NP, but in this case, N is 26, and your success probability is 0.4. And whatever that was, a quarter of 20, no, about half of, anyhow, I get, it's 10.4. And the variance, what was the formula for the variance? This is going to be,
P1 times P.
yeah, it's NP times 1 minus P. Now, if you're taking GE stats, there's always a square root over that whenever it shows up. Why is that? Because when you standardize, you subtract off by the mean and divide by the standard deviation. So that's sort of a hard habit for me to break because I've taught 140 for, since before my hair went gray or lost. And that's why it went gray. No, I'm kidding. So NP, I already know what that is. And then that's going to be multiplied by what? 1 minus P for 0.6. So let's see. 10.4 times 0.6, I did this, or copied out of the book, I forget which, but it's 6.24. Now the other team, so E, going against the other guys, the easier ones. So how many games are the easier? They had 18 easy games, and their probability of success was 0.7. So that's 12.6. So this is 12.6. I hope I can not make a mistake somewhere here. And the variance would be what? XB is NP times 1 minus P, but that in this case is 0.3. So 30% of 12.6 is 3.78. Okay. Now, what do we need to do? Now I have to use, I'm going to have to use that theorem, but I need a little space here to operate. So assuming there's no question about this, we've done all this binomial thing, numerous times. The only twist here is that we're going to we're going to approximate with a normal, with normals. So what is the thing that we want to realize? So okay, so we're sort of assuming that these binomials are, we're assuming they're normal. Okay, but with what? They've been approximated by a normal distribution, and they're going to be, what will be that sum on that? So it says to add the two means. And what were those? So I can do that in my head. So the two means is 23. These two means are here. And now I've got to take the sum of the variances. So what is that? 10.02. So this is assuming that these have been approximated with a normal distribution. So now that we've done with this application of this theorem here. So what? So we want probability of W, the total number of wins greater than or equal to 25. Well, we've got it into these two. They're still binomial at this point, but they will be momentarily. X, you want this to be greater than or equal to. Let's see, it matters whether it's greater than or equal to. Here it was 25 or more wins. And so what we want to do is, okay, now we're using this continuity correction or something. So if we're going to normalize, we need to capture the 25, we need to go down halfway to the next mark. So we have to go down to 24.5. Okay, that's the continuity correction. And now we are going to standardize this variable right here. Okay, so standardizing, so this is what? The probability, okay, this is the variable minus the mean over the standard deviation. And we have to do the same thing to this. We're doing the same thing to both sides. So it's 24 point, hold on a second. So greater than or equal to 24.5 minus the mean, again, same thing. I haven't been looking at the chat. Maybe I've been totally disconnected now for chat is empty. I hope you guys can hear me. It's not.
Fine.
Okay. So where do we use this? Okay, so well, okay, so this. Where was I? So this probability. So this is approximate. Okay, just lost the train of thought for a second. Where did I use? So I'm really saying that this is this, but where is it happening? Because it's not happening at this point. I think it's happening at this point. So I should have put. I think this is approximate. And what is this? So it's the probability of a standard normal. This has been normalized. This we already know this is a normal with that mean and this standard deviation. I mean, that's we're making that as from the theorem that was there prior. So z is greater than or equal to, what is that on the top? So 24.5 minus 23 is 1.5. over this square root. I don't know why I'm keeping the 0.02. That's the book did, but it's so. I calculated this, and I think I didn't get the same answer as the book. Maybe that's. Let's see. So this is the probability of z greater than or equal to, what is that number? I'm getting approximately 0.47. So that's approximate. And so okay, so how do we do this? Number is a review. How do I get this? Where's 0.7 on the standard normal? Well, this is 0, this is 1, so 0.47 is right here. So if you're looking at, if you're looking at this is 1 here. So if you're looking at this stuff here, that would be what? So red would be equal to 1 minus cumulative CDF of 0.47. So I've got to find out what that 0.47 is. And I did that at home. I got 0.68. I should probably check it. The 0.68. Okay, I just checked the book. So the answer to this, its approximate, is 1. 1 minus 0.68. And what is that equal to? That's approximately 0.32. Now, I should double check. I did a couple of problems out of the book, and I did not get the same answer in the back of the book. So I'm a little nervous about, checking these. But since this was an example, the answer should be right. Let me just check with it on. Okay, they got 0.32. Now, on the test, there's a different thing. They want to know what is the probability that one is bigger than the other. Well, you have to. Okay, you're going to have to integrate a region or something like that. You have to. Your variable will be okay. On the test, your variable is something like x minus y. But you've got to understand that if you have x minus y, it still fits into the model of that theorem, because it's x plus minus y. So minus y has its mean is just negative, or the other one is, but it's got the same standard deviation. So if you're translating a bell, it's going to have the same variance. Okay, it's not going to change, but it's of course its mean will change. So just be aware of that.
On our test?
Yes, because
our test is the bowling problem.
Okay, final exam. I was going to put that in.
Okay, well, now we know.
Yeah, you want that if you have the different, right? Because it's a better question. It's a better question to say one player is not as good as the other player, and then what is the probability that the lesser player beats the better player? And you take the difference of the two random variables, and then you can use the same theorem there. That's what I'm saying. The variance stays the same. The calculation for the variance is the same. Yeah, I think when I made this test, I just tried to hold back. I don't know. Maybe I held back too much. I made the problems too easy. But
considering the fact that we basically have a week, I feel like that's fair. Like,
no, I know. No, that's what I'm saying. I'm saying, look, we're at the end of this thing. Let's just get this over with. Yeah.
There are still some people who are trying to write down what's on the board. Okay, awesome. Anyway, my question is, so for the coin toss problem, which has 25,000 coin tosses, or 50,000, and then the bowling problem, would you like us to do a continuity correction?
It's not going to make any difference.
Yeah, really.
Please do it, just so I know you know how to do it.
Okay, sure. It's
not going to make any difference.
Right.
It's whatever, I was not particularly sharp when I made it. I should have had it closer to 25,000, but it's just, it's something to do with the law of large numbers, that
right.
The ratio is going to be getting closer to, and, that's just the way it goes. So, again, being in a hurry and slapping this test together. So, yeah, if you feel it's fair, then I feel, hey, man, that's good. I just don't want to embarrass anybody with problems that are too easy. But I think it's the first problem. You'll have to look at CLRS maybe, to see, well, how do you prove it? So to me, that's a legitimate web search kind of activity, for a test. Unless you can do it. If you can do it on your own, power to you without looking at it. Power to you. Yeah, I'm talking about the little code, the pseudocode, the ERP. If you can prove that that's an ERP, just using our notation, I think that's fantastic, But I'm not expecting, look, this is an open book test, and we've mentioned CLRS so many times that people can drift towards that source. Okay, so what else was I supposed to do? Now that I've done about nothing. There was stuff from. Hold on, I have to find them. It's very, very, very unorganized today. Hold on a second. Looking at the previous chapter, there was a hole. There were some holes in 5.7. Okay, let me check the chat. There actually is somebody's got a chat. Let's see what that says. Can't see. Okay, but you got it now. I hope. This is a dual approximation, right? We started with binomials. We got approximated with the normal, and then those normals. Then we were able to have a theorem on what would be the distribution of the sum. The sum is sort of like the easiest combination of things you can get, but it's not simple. Okay, it's some sort of convolution or something. You have to take to these continuous things. But we've already done sums in the first test. Remember the sum of those indicator functions. We have done. We didn't prove anything. But we used the fact that the expectation was linear. So we looked at sums of indicator random variables. So it's like we've done this thing, but it was sort of in a kind of a not a very sophisticated setting. All right. Okay. So there was some sort of hole that was. If you look back at 7.1, there were some examples there that I wanted to cover. So 7a. So x equals uniform 0. Now we're back to just one random variable, and if y equals x to the n. So this is a function of the random variable. And the question was, first of all, the y's, what's the space of y? So, x goes from 0 to 1. So y's are in this range. And we want to know the distribution of y. Okay, so what does that mean, the distribution? What do they want? Okay, when we have continuous random variables, what they want is that density function, okay? So that's small case f of y. So we're looking for the density function. So in other words, that is f of y. Okay, so what is the technique for this? Well, the technique that they use in almost every time, it's not the only way to do it, but they get the CDF of y. So the probability of, they try to calculate this. Now it's a little bit of a joke, but sometimes in the book they put x, and sometimes they put y here. And I can't figure out when he's going to put one. It doesn't matter, it's a dummy variable, but I can't figure out, he's not consistent, which is weird because he's consistent, through the generations, right? We're on the 13th edition or 12th edition or something. So what is this? This is the CDF of y. So what is that? That's the probability that when variable y is less than or equal to y, and that's the same as the probability that x to the n is less than or equal to y. So you're converting this into a question about the distribution of x here. It's what's going to happen. So what is this? I'm going to be somewhat careful here. So x is less than or equal. Why do I have to be careful? Because if x was allowed to have negative values, weird stuff can happen here, okay? So remember, x is non-negative, okay? So it's, I have to be careful if, we're taking roots if I have negative things. Okay, so what's the next step here? So this is from 0 to 1, 0 to y, the nth root of y, of, well, what is the density function of x? It's just 1 on between 0 and 1. So it's 1 dx. So that integrates to y to the 1 over n. And then if I want to get the density function for y, what do I do here? I take the derivative of this. And what is that derivative? Well, it's the derivative of y to the 1 over n. So this 1 over n, y to the 1 over n minus 1. So I was telling you that you have to be careful about when there are negative things and you're taking square roots. In fact, square roots are a misunderstood thing in math. I mean, just an aside, some people say that they think complex numbers are the same as real numbers, but because when complex numbers, I'm just an aside, just take a break for a second. You know that I squared is minus 1, right? Well, so if you were to take the square root of I times I, the square root of minus 1, that's I. Hold on a second. Let's start over again. If I take the square root of minus 1 times minus 1, this is clearly 1. But you can break the square roots, the property of square roots. And the square root of minus 1 is what? Well, that's that symbol I, right? So these are both I, and this is minus 1. So who knows what's wrong with this? Who knows about complex numbers? What's wrong with the reasoning here?
I guess this property of splitting square roots doesn't apply to complex numbers? I don't know. I'm actually not sure of why, I mean, clearly something's wrong. We can't have y equals negative 1.
Well, see how I started this in red, because you're right. I mean, people think, the way complex numbers are taught is very, how should I say, superficial, sort of, we just do this and this, we do this and this and stuff like that. And the thing is, the actual problem is the function, the square root. Because when you allow complex numbers, it's suddenly now, I don't know how to say this, you have to take a so-called branch of it. You can't. There's two square roots, right? So you have to decide. It's a sort of a complicated affair to describe the square root of a complex number. You can't just. You have to know which square root you're talking about here. You have to specify that, and it's going to be a shock to even people who have had complex variables, because they just steamroll through this thing and they forget that you forget that precautions have to be taken, because there's actually just many square roots. But oh well. I'm just saying that it's whatever. I don't just. You can think about it if you want, but the problem is that superficial learning doesn't cut it for that. Now I've forgotten where I was. Oh yeah, so now there's an example where you do have to take the square root of something squared. So there's a slight generalization now. So instead of this, we'll just say there's some x that has some random variable that has this density, okay? And y is what's going to cause the trouble here. So y is x squared. And now we'll just try to answer the same question. So try to do the same thing. So I don't know that anything has to be changed here. Make sure I've got the right question. The only thing I changed was that this is sort of an, there's some random variable x that has this density, and it's not necessarily uniform. I got a question here. Wait, for reading later, somebody like exchange questions about somebody says questions about can't see. Well, square root of a complex number. Okay. Well, look, you guys. I mean, forgive me for saying it. Okay, I brought this up in the algorithms course at the end of the class. Okay, so I wasn't taking any class time like I hogged here, and I had people who had taken the complex analysis course and they didn't know what I was talking about, and there was a complete meltdown. And I don't know. It's funny, I mean. It seems to me when you take a class, they discuss this stuff pretty early in the book. The square roots, branches, square root, whatever. They talk about this stuff, and that person who took the graduate course, I think the graduate course in complex variables, so somehow they didn't get that part didn't sink in, and then there was a meltdown, a big, a huge meltdown. So with some trepidation, I gave you that example. Okay, so what do I have to change? Do I have to change anything here? Or where does the change come in? Instead of n, now it's 2. So we're going to be careful here. That's a 2. So now, when I take the square root, I've got to be careful at this point, because what am I going to get here? It's the absolute value of x is less than or equal to what? The square root of y. Why didn't I have this complication before? Because things were positive. X was uniform from 0 to 1. But now I've got to be, there was no, this is just an arbitrary, we don't know what that density function is. It could have negative numbers in its space, the random variable. So what do we do now? Well, let's try to analyze this. If the absolute value of some number, say it's less than or equal to 2, what are we referring to? I know this is elementary, but I just don't want to. What are we referring to here? It's this, right? So this would, knowing this, how would we write this in probability notation? But first, let me erase this, because this was something to do with the previous problem. Okay, tell me how to write this. What does that mean, seriously? If the absolute value of x less than 2, well, I can express this interval as what? That's minus 2 less than or equal to x less than or equal to 2. I know you learned this in pre-calc, but I'm telling you, it causes trouble when I'm teaching this course. So this means, what are we talking about here? The probability that, what? That minus the square root of y is less than or equal to x is less than or equal to the square root of y. All right? So how to finish this? So this now is in terms of we can write things in terms of the CDF of x. So how can we do that? So this equals, well, you can start with the CDF of x of square root of y. That would be everything. minus the stuff that's to the left of minus squared y. Okay, so this is like doing a normal calculation, right? So you want to get this interval here. So you take the CDF up to 2 and you subtract off the CDF up to minus 2. Is that okay? It's awfully quiet, but this is just messy stuff that I have to do. I've no choice because I know that they do things like this in the stat course that follows. Now we have to take the derivative. So this is f sub y of y. So what we need to do is take the derivative. So if I take the derivative, what do I get? And hopefully I have space to put it. So I get the f, the derivative. That's f sub y. Darn. And that's going to be what? Now, I don't know if I have space to put this. This is taking the derivative with respect to x, we get what? So f of x and square root y times 1/2. You know what? I'm not going to have space to put this. So this is just unfortunate. I have to write it somewhere. And I don't want to do it in red. Let's do it over again. So what do we have so far? F sub y is CDF of x square root y minus CDF of x minus square root y. I've got that. Now what I need to do is take the derivative. So that's f of the density of y will be this derivative here. So this is f of x at square root y times it by the chain rule. Derivative of this, which is 1/2 y to the minus 1/2 minus this guy, f of x and minus square root y times this derivative. So it's minus 1/2 y to the minus 1/2. Okay, and you can clean this up, I think, by pulling out this. Okay, you can clean it up by these two minus signs will cancel. And then they have this is in common to both of them. So this is 1/2 square root of y times f of x square root of y plus f of x minus square root of y. Now that seems like a lot of mucking around. This is simple things, but the purpose of this is what we just did and what we did and what we might be doing in a second, they're all special cases of this can be a hit with a theorem, okay? And I'm very resistant to just spitting out theorems without giving some type of motivation, okay? So these three examples together are supposed to be motivation for the theorem that comes. I'll give you that theorem on Tuesday, okay? And then Tuesday I'll have to start, I got to start the central limit theorem. I'm not proving anything, I'll just tell you how to use it. In the Chebyshev inequality, these are things getting bounds on probabilities. Well, the Chebyshev Markov's inequality, just getting bounds when you don't have a lot of information. All you have is the mean and the standard deviation. There's a lot of distributions that are going to have a certain mean and a certain standard deviation. It doesn't have to be a normal curve, okay? So if you don't know what your distribution is, you can still do probability and statistics. Okay, so what was the third example? So this was the second example. The third, what would it be? Okay, what's the last thing I didn't check? So we did x squared. The first one was x to the n, but the distribution was the uniform. What's the only distribution I didn't do? Okay, so what's a simple function involving these players? What's the simple function? Y equals x is the same distribution, but how can we modify that to get, what's the simple function that we could hit it with? Which you actually have on your, it's something, related to the test, those two waiting times, or those midpoints. So what would be a simple? So what's this? What are the simplest modifications of x I can make? Think about that. So what? Okay, well, x squared we did. Okay, we could do e to the x, which I thought I did before, but that's not simple. But what's a simple? If you got x, what's a simple function of x that we might encounter? I think you know it, right? You know what I'm thinking.
2.1 is the uniform. Okay.
Just that, how's that going to change things? We're moving kind of slowly here, but all these cases can be covered by the theorem. The function has to be okay. The function has to be 1-to-1 on the interval of concern. So x squared, obviously, you're going to start that at 0-to-1, and this is not. So this one, you're going to have some condition. Well, let's go ahead and dive into this. We know what we want. So do it the same way because the probability that y is less than or equal to y. And so y here is absolute x. Now, how do I interpret that? So it's the same thing. It's the same thing as before. It's the same thing. So I don't understand why. So this is probably that x of j minus y and y. So yeah, what's the difference? Sorry, I just forgot what the difference was. It's very similar. Yeah, in fact, it's too similar. Okay, it's the same. Well, I don't know. Maybe I just don't remember where the difference is. So you're going to take f of x and y minus f of x of minus y. And then to get the density, I'm going to take the derivative. And what's that going to be here? So it's f of x to y minus f of x minus y, but then I have a minus 1 here. So it should be a plus at the end. Yeah, these two minus signs cancel out. And this is valid for y between 0 and 1. Okay, so the theorem that I'll cover next time is theorem 7.1. It's a little complicated. You have to. There's some condition on the whatever the function is of the random variable. Okay, so let me get back to. Let me just see how much, time I've got here. Find my phone. Oh, here we go. Now we got time. Okay, so let's go back now into the joint distribution phase of things. So let's just let me check the chat. Okay, so these three examples, even though this example is almost identical to the prior one, they all lead ins to this theorem here. So when you're doing change a variable in the next class up, they just hit it with the theorem. They don't go through all this long process here. But the theorem its proof incorporates these steps. Okay, so let's just do a couple review things. But just calculational things. Find it. Okay, so this is trickier than it looks. It's not so simple. I'm in chapter 6 now. So back into the current chapter. And this, you have a joint density function of this. So 2 e to the minus x, e to the minus 2y. If you're in the positive quadrant, and 0 otherwise. Okay, so can I ask you this question before we do the problem, or even state it? Are these two random variables, x and y, are they independent? And if so, why? Just think about that and I'll write the first question. So the A part is the probability, we want the probability of x is greater than 1 and y is less than 1. Okay, so what did we say about independent random variables? If they're discrete, what do we have? What do we have? We had p, x and y of I, j for all points of mass is what? It's what? P of just the probability mass function for x, I times the probability mass function for y and j. You had to have this happen. This has to happen for all points of mass, okay, where there's positive probability for that outcome. This is the condition of independence. But what's the condition when you have this continuous thing? So look at this. What would be the condition here? Well, if the joint density factors into a function just of x alone times a function just of y alone, that's the condition. Then they're independent, okay? So this is a case where they're independent. And this is sort of critical because just let me use a different color. Just if you have a situation like this, so it's a double integral f of x, y, dx, dy, something like this, so over some region, you're going to have a hard time doing this as an iterated integral unless you can split that f function into an x and a y, because it's only in advanced calculus where you do integrals that don't they can't be iterated. So it's something you've got to look for in a problem where they say these x and y are independent. Well, you can split this. You can split it.
So if you can split it, if like you can have a function of x times a function of y, yes, it's for sure independent.
That's the definition of independence. Yeah, if you take that as a definition. And I'm telling you, almost every problem you have in the entire book, there's this assumption of independence. Otherwise, you can't calculate. You've got to. You're integrating over something. It's just a 2D. What do you call that? It's a multiple integral, but you can't break it down. What's it? Fubini's theorem that breaks it down into iterated ones. But let's see if we can do this one right here. Does this have any relevance to the problem on the test, to the transistors? In a trivial way, right? I mean, if it takes the i's and the j's are intimately related because the n1 and the n2, because if it takes a long time, if n1 is big, then n2 has got to be smaller, right? Because you only have a total of 6 draws before you know everything. So obviously, in the transistor problem, it's, you know, there's no intent to deceive you into thinking that it's clearly not, it's clearly dependent. But there are some problems in the book where it's more delicate. Okay, but let's see what we can do with this one. So again, this looks innocuously easy, but it's not so. How do I get this problem? What region am I talking about here? I know that the random variables are here, but what region is there? We have to figure that out. So x is bigger than 1, and y is less than 1. So what's the region? X is bigger than 1, so I'm going this way, and y is less than 1, so I'm going like this. So it looks like this, going forever that way. So tell me then, what is this probability? So what is it? What is this? So they get this. Okay, so I got to decide what I want to integrate by x first or y first. I want to align with what the book is. Let's do with respect to x first. Okay, let's put the density in there, 2e to the minus x, e to the minus 2y. Now comes, this is the critical thing, okay? Which even the check tutors sometimes mess up. So y is going between what and what? Y is going between 0 and 1. But what about the x? So the x would go from 1 to infinity. This is this infinite rectangle here. Okay, so to get the answer, I just have to separate these. So this is some technique of doing basic calculus, but okay, so what is the technique? So let's put the y stuff is moving out of the way, and now I have to integrate this e to the minus x. So the integral of that is e to the minus x over minus 1. And I have to go from 1 to infinity. All right. And okay, and then what? What is that piece equal to? I just have to make sure I don't do something silly. So the integral of this is minus x over minus 1. The 2 has already been moved out. So what is this? What's this evaluate to? Let's just figure that out right now. Infinity, it's 0. And 1, so it's minus evaluate 1, so it will be e to the minus 1. Right? Because infinity is 0, subtract off the value of 1. That means these negatives cancel. So e to the minus 1. Are we good? Sorry, my calculus is a little rusty because I've never, at CSUN, I've never taught the calculus course. So what can we do here? So we have e to the minus 1 times, how do I integrate this guy now? So e to the minus 2y over minus 2, but that cancels this, so there's a minus there. And that's from 0 to 1. What am I shooting for as an answer? I don't want to make, it's e to the minus 1 times 1 minus e squared. So e to the minus 1 times 1 minus e. E to the minus 2. Well, let's check out and see if that's right. So I get the e to the minus 1, but then it's this and 1, so it's minus e to the minus 2, minus, so that would be plus, this plus 1. And that's what the book has there. One of these, though, was tricky. It evidently wasn't this one, but one of these, A, B, C, D, whatever it was, there was something tricky about it. Okay, so let me answer this question. So what if you want to get a marginal distribution? Let's just a question. Let me check the chat. What if you wanted to get a marginal distribution? You know, so I don't want this joint CDF kind of thing. I want the marginal. Just how is f of x, just f with respect to x? How is that what's the distribution with it just for x, the random variable x? How would I do that? So let me. Okay, because that's going to require integrating out the other variable. Okay, just like we did in the discrete case. How would you calculate the probability of x less than a? What do we need to do in this case? Well, I need to integrate out the y. So the y's, that was the region, right? The y's go from 0 to 1. And this, okay, so these x's there's nothing that this density function is 0 off of that positive quadrant right here, quadrant 1. So I want to go from 0 to a on the outside 1 to e to the minus x, e to the minus 2y. Okay, so basically want to wash out this y stuff here. Let me check the y. I'm looking at this other problem. This is not our problem. This is the problem here, x less than a. So really I should have been more awake here because the y's, this is the positive quadrant. So all of this stuff is counted in the probability of x less than a. So really should have put infinity here. Sorry, I was looking at the wrong thing. So when we wash out the y, so let's see, what will it be? 0 to a, 2 e to the minus x. Now I have to integrate this y here. So e to the minus 2y over minus 1 from 0 to infinity dx. So what is this equal to? I'm stealing this 2 over here. So this is 0 to a, e to the minus x. And then what's this quantity here? So infinity minus will be plus, it's 0, 1 dx. Darn it. I did something dumb here. Hold on a second. I've got my limits mixed up. So the y, that's wonderful. It should have been 0 to a. Sorry, my eyes are not good enough to see. To me, this is right.
Where I'm confused is whenever you went to e to the negative 2y, you integrated y, there's still a 2.
Right, I stole that 2 from the... See, you have to put a 2 down here, right? To make that happen?
Right.
You have to put a 2, but that 2 cancels with this 2.
Okay. Oh, I see. Okay, you canceled it already.
Yeah, that's what I was stealing the 2. I mean, I was multiplying the 2s you get. So that goes to, so they cancel. Yeah, they cancel each other out. Sorry, I basically took that 2 over here and pushed it into this to. But what is the answer? So it's e to the minus a minus I think I've killed a minus sign is. Oh, okay. I need to be very careful about this. Let me. I got to integrate this. This is e to the minus x with a minus 1 underneath from 0 to a. So if I evaluate at a, it's e to the minus a minus. If at a, it's going to be e to the minus a, but there's a minus sign in front of it. Minus 1, so plus 1. So what's the final answer? Okay, so the final answer is 1 minus e to the minus a. Sorry about that. I'm a little rusty on doing the, especially with the integration of, it gets the integration apart. Since it's separable, we can take. That's what we're doing, right? Right. I mean, that's what we did, right? It was a double integral, and now I've broken it into two things, right? Right. I mean.
Yeah. No, you're fine. I'm just making sure that I'm doing my math right. Like I'm trying to do the problem alongside.
Did you get the same
I got 1 minus e to the minus a.
Yeah. So, but this is the thing that's different about this is that you're integrating through by the y. So you're getting the marginal. If you go back to the discrete case, you're getting the marginal distribution.
So the idea being take y and integrate over everything that it can possibly be. So in this case, from 0 to infinity.
Right.
And so you won't have, once you've done that, you won't have y anymore. And then we integrate for x just from 0 to some variable.
0 to a, because this is what we're dealing with is the.
Okay. Well, yeah, they gave us the a, yeah.
Yeah, they give us a, but it's a CDF. So what you're doing is evaluating some CDF here. So, but you integrated out the y, so that's no dependency on y. I mean, the other thing is to picture that. Remember that example I gave where the red balls and the white balls and stuff. You're integrating across a row there. So you're taking the y out of it. You're looking at if it's just a function of x. So that's happening. Let me check the time again. I may have more time. I don't know. Oh shoot. Okay. I've got 2 more lectures, and I want to touch on the CLT, the central limit theorem, and the Chebyshev's inequality, but mainly the CLT for anybody who's going to tutor statistics. Math 140, that's quite a bit of demand, and it's you do it privately, there's no tax, stuff like that. But you have to know the CLT, and they always give problems to these GE people how to do it. They're just plugins to the formula, but you got to know the relevant theorem, the statement. So I'm going to try to do that in on Tuesday and Thursday, but also maybe fill in still a couple things that I like to look at in chapter 6. Just a couple things, maybe some problems in the back. It's very interesting. The number of problems is low in chapter 6. So that I interpret that to mean the theory is very dense and very hard, and they can't really illustrate it with problems. So there's no sense, in just putting more problems that are just plugins. But thank you for enduring that. I just know for a fact that if you're going to take 440, I don't know if it's called 440A now, whatever it is, it's the stack course. They run you backwards and forwards on this what do you want to call it? Change a variable, integrating stuff, and getting the moment generating function, which is another integral using by parts. It's just they're going to make you do this, which I don't like to do. I like to do problems where the intuition, carries the day. But one thing for sure I like to do is the sum of 2 uniform distributions. I want to get that tent function, that triangle. So that's a convolution. You have to integrate something. It's called a convolution. That shows up all over mathematics. So we should do that for sure on Tuesday before we talk about the other things. All right, guys, been very polite. Good luck on your test. Is anybody coming to me in the office hours, the late ones? Is anybody going to be there? Just
is that 6? Or what time was it at?
6:30 to 8. But if nobody shows up by 7:10. Usually I shouldn't.
Yeah.
I usually just say, hey, they didn't tell me they were coming. They just nobody's there, so I kind of go my way. But if somebody tells me, hey, yeah, I'm going to come in there with problems A, B, C, then I need to be ready.
Okay.
But it sounds like you guys are okay. The test is just,
The test is doable. I'll say that. Problem number 2 I sat with for way too long, I feel like, but
what was that?
I got it done.
What was that problem again? Just remind me.
That is the one with the 2 line segments that were of length 2, and
yeah, that's an absolute value of x minus y is less than or equal to, right? It's just like we did, right? It's kind of kind of like we did, right? I mean, we did with the waiting time. Remember the waiting time problem?
Mm-hmm.
But the figure you get is not well. You can do it without writing integrals, but this is
right.
You have what do you have, a trapezoid? What's the area of a trapezoid? The area of a trapezoid.
Right.
Or you can take the difference of 2 triangles, but whatever.
Mm-hmm. But yeah, I got it done. We're at the point of just typing it up. Really, we're good to go.
You're not at the point of no return. No.
Yeah, thankfully. Okay.
Okay, so I try to make the final reasonable, and I hope good luck on your other classes. I have no idea how you're doing with everything else on your plate.
Oh, it's busy. I have another professor who does take-home tests, and he assigned it at the exact same time as yours. I'm like, dang it.
Let me guess. Is that Emmanuel?
No, that's Jerry Rosen.
That's interesting because he never does what I do. He never follows.
I have a feeling it's more just with the online format. That's just how he'd prefer to do it. I don't know.
What class is that? 360 or something? Or
it's number theory, 463.
Oh, that could be heavy duty.
Yeah, exactly.
That could be really complicated.
Yeah.
You did the Chinese remainder theorem and applications and all that?
Yep.
The prime number theorem or no?
I don't know about the prime number theorem. It's a lot of primitive roots right now.
Mm-hmm.
And quadratic residues and stuff. My brain hurts. That's really what it is.
The quadratic reciprocity.
We're doing quadratic reciprocity.
They knew about it for a long time. People knew, but nobody knew how to prove it. And they had to wait till Gauss came along, and I think he gave 3 different proofs or some crazy thing like that. And but they needed to wait for a genius to crack it. They knew that people knew patterns, right? And they knew that there's something there. They just didn't know how to show it. Did you prove it in class, the quadratic reciprocity theorem?
Yeah, we did. I think. I'm pretty sure.
Yeah, that's heavy. That's like a whole lecture, right? I mean, that's
it was a whole day. So, yeah, it's fun. I might. I'm gonna try to make it to office hours at 7. Okay. But yeah, I got just a couple questions. But yeah, I'll see you then.
All right, nice seeing you. Where's Ethan? Ethan disappeared. Okay, Luis, it's good to see you. You're there.